So, okay, Chetan has a question about the homework. Okay, so if you have done a mistake in your homework and you've uploaded it already, you have to let me know by email so that I can delete that particular response and you can re-upload it. Okay, so I think for the first homework, Zabula, someone, I'm not sure, Zabula, I hope I'm pronouncing her name correct. She let me know that she made a mistake in her homework. So I deleted her response and she was able to upload her homework again. So that's something that you could do. So if Chetan, you have a problem with that, I'll delete your response if you have submitted it already. And then you can re-upload the correct version. Okay. Also, one more thing, I went through your homeworks yesterday for the first lecture, and all of you, most of you, except for a handful of 5 to 6 people, all of you copied the homework. And do you know how I got to know that? Because all of you copied the same mistake. So in the fourth order Ranskara method, what you have done is you have all copied the second order Ranskara value for the second iteration. And all of you, I was really, it was sort of easy for me to correct because I just had to look at the table and I could understand that all of you have copied. Okay, except for a handful. Some of you have actually sat down and tried to do it and have made a mistake. It's fine. But all of you having to copy that same value, it sort of shows like you're not in second grade or whatever, right? You're MSc students, right? So you're supposed to be doing the homework on your own. If you have difficulties, of course, you can get back to me. That's always there. But, last minute trying to copy the homework down, I mean, like, if that's the case, if you guys are going to copy the homework, don't submit it. If you genuinely want to understand what has gone wrong with your problems, then submit the homework. The reason I'm bringing this up is because I got a question about the homework. So I recall all of you guys, literally all of you guys, except for a handful of 5 to 6 people, all of you just copied it. Okay. And when you copy it, you copy the mistakes as well. So you don't even check it. Okay, fine. You want to compare it with another person, fine. But then when you work it out, you're supposed to be working it out on your own, right? And the decimal places that you've used. So the first one has up to 4 decimal places. The second iteration value has up to 3 decimal places. Again, the third iteration has up to 3 decimal places. So please keep in mind the decimal places. If you're using 4, use 4. If you're using 5, use 5. And be consistent with that. Even if you don't have the last decimal place, say you have a value, say like, let me just put that out. Okay, so if you have a value, say 2.390 and 0.5, and then this part that you have is still 0. Okay, so just because it's 0 does not mean you don't write that 0 down. Try to be consistent with your format. Also, if possible, write the questions in order. Okay, the reason why I say this is because people who are correcting, the faculty members who are correcting, they are literally bundled with a lot of papers. So if you write them in order, they don't have to go through the whole process of like flipping the pages and stuff like that. So yeah, I will probably do a session entirely on your homework solely, but I just wanted to say this because I was pretty disappointed. Just 5 to 6 people of you have handed in the homework. That's really genuine. And I can understand that you've actually worked it through. Rest of you, all of you copied it out. Okay, if it's not compulsory, you don't have to submit the homework if you don't want to. Okay, the only reason that I'm asking you to do the homework is because it's easier for you to learn towards the end of the whole thing. Okay, so if you don't want to submit the homework and if it's not your genuine homework, don't submit it. Okay, if you want to learn something and if you want to do it really correctly, then do submit your homework. Okay, so now what I'm going to do is I'm going to mute all of you. Okay, if you do have any questions or if I haven't addressed them properly right now, you can get back to me about that towards the end. Okay, so what we're going to do today is we're going to do the remaining section that we have of the Gauss Legendre integration method. And we are also going to start off and finish a new section on Legendre polynomials and computing Legendre polynomials using recurrence relations. Okay, so let's just look at one of the homeworks that I gave. One of the homeworks, I think, yeah, one of the Google forms I gave last time had about 3 questions. So I'm going to just repeat that again so that it kind of like refreshes your memory, and then we will go on to doing it for arbitrary intervals, say a, b, not just from -1 to 1, for arbitrary intervals. Okay, so what was the summary of all the formula? So please take this down, take a sheet of paper and take this down right now, because you're probably going to be referring to these formula. Okay, so the summary of the different Gauss Legendre point forms. Okay, so this is the 3-point form. Okay, so you have your 5/9 function of -√3/5. So you have to include this value in that particular function that you have. You need to calculate the integral you need to calculate. And then you have 8/9 f of 0 plus 5/9 f of √3/5. So you have 3 points here. Therefore, it's called the 3-point form. We discussed this last time. Then you have the 2-point form. So the 2-point form, you have -1/√3 and +1/√3. Integral from -1 to 1 f of x dx. So these are the 2 points that you have to evaluate it at. Okay, so you don't have any, well, the lambda 0 and lambda 1 that is associated with this is 1. So it's pretty easy for you to remember this, a comparison to this. Okay, the next one you have is 2f of 0. Okay, so for your 1-point form, which you have is 2f of 0. Okay, so this is a problem that we had. Okay, the thing is that in the question paper, they will only say evaluate the integral, and they will just say using Gauss Legendre method. They wouldn't mention 1-point form, 2-point form, or 3-point form. Okay, so you need to be able to do this for all the 3 different forms, and it's pretty trivial, right? You just have to plug in the function and the points, and then you get your answers. Okay, so your f of x is equal to x squared. Using your 1-point rule, what do you get? You get 2f of 0, which is equal to 2 into 0 squared, which is equal to 0. Okay, so this is pretty simple for your 1-point rule, but this is not the actual value of the integral. Please note that this is not the actual value. Okay, the actual value is 2/3. Okay, so once you calculate this, we did this last class, so it's just a review. Once you calculate this, you get 2/3. Now, what do you do for the next one? You use a 2-point rule and you substitute the value of the, what is the value of the function? The function itself is x squared. So you do -1 divided by √3 whole squared plus 1 divided by √3 whole squared, and then you get the value of the integral as 2/3. Similarly, you do it for the 3-point rule, and then you get 5/9. You just have to substitute this. So here you would have to substitute the value of x squared. Okay, so this is basically an f of x. I hope you get that point. So you substitute the value of x squared, you get √3 divided by 5 whole squared, and then you get these values. So you end up getting a 2/3. Most of you answered it correctly, but some people still, I think you're basically clicking in the values for fun or whatever, but yeah, I'm trying to do my job as best as I can. Okay, so I will start off with a poll. Okay, this is a revision. I hope all of you get this correctly. Okay, because we've discussed this several times. In the Gauss Legendre integration rule, the interval is restricted to -1, 1. Is it true or is it false? Okay, so I will start the poll now. Poll number 16. Okay, so this is a Gauss Legendre integration revision question. So please poll in your answers. Please poll them in fast. Okay. Okay, good. A lot of you are quick. Okay. Somebody answered false. Please poll it in fast. You've got 30 seconds left. $20 seconds left. Can I get full strength? 4 more of you have to attend the poll. Okay. 3 more of you guys. Okay, fine. I'm ending the poll now. I still don't get it. 6 of you still answered false. This is a question that we've discussed at length. Okay, just don't click in the values because you know you just want to just finish off with it. Okay, what did we talk about? We talked about in the Gauss Legendre integration rule, we talked about it is restricted to the interval -1, 1. And I told you there's going to be a problem where you can do it for an arbitrary interval, say a, b, right? So the answer is true. It is true. It is restricted to the interval -1, 1. And I don't get why 6 of you have still answered false. Okay, so I'm just going to go ahead with it. Please review your material. Okay. Okay, so let's move on. Okay, so now we're going to be discussing it for a general interval a, b. Okay, so the Gauss Legendre formula for the general interval a, b. What are we going to do? We are going to be transforming from a, b to -1, 1. And what transformation are we going to use? We're going to be using a linear transformation. Okay, so first we will assume that you have your x equal to p of t, pt, not p of t, pt plus q. Okay, and then what we would do is we would find P and Q in terms of a, b. And then we would try and substitute this back. So we get an x function, okay, a function of x transformed into a function of t. Okay, and then we would do your df, or we would do dx rather, so that we can replace it with dt. Okay, we would be replacing dx with dt, and then we would get a function in terms of t. So what are you basically doing? You're converting a function f of x that you had, your integral. So you had integral from, say, a, b. You had a function f of x dx. You're going to be converting it from -1 to 1, f of t dt. Okay, so that's what you're going to be doing. You're converting. So I wouldn't write f itself. I would write some kind of like other function g. So you're transforming from x to t. Okay, so what transformation are you using? You're using a linear transformation. Let me just be very particular on that, linear transformation. So let the transformation be x is equal to pt plus q. When your x is equal to a, what do we have? We have t equal to -1. Okay, and I'm sure you must have done something like this when you did your integrals in your BSc. You would have done some transformation from a particular type of particular bound to another particular bound, if you probably recall correctly. Okay, so when you have your x is equal to a, your t is equal to -1. So what do you get? A, your x is a, so you substitute a here, minus p plus q. Similarly, when your x is equal to b, you have t is equal to 1. So what is x? B, and t is what? 1. So b is equal to p plus q, and here you have a is equal to minus p plus q. Now what do? You need to solve these two equations for the limits that you already given, for the limits that are given to you in the question. So you have p is equal to b minus a divided by 2. How do you get that? You just have to add both of, you just have to subtract both of these rather. Okay, so if you do b minus a, you get 2p. Okay, b minus a gives you 2p. These two get cancelled out, right? So b minus a would give you 2p, and then you would get p is equal to b minus a divided by 2. Here, what would you do? You would add both of them up. So if you do b plus a, you would get 2q. Okay, so b plus a should give you 2q because your minus p and p gets cancelled off. Okay, so once we found p and q, what do we do? Okay, so just remember this, there are 3 steps to the whole thing. Okay, so in the first step, you have 6 sub-steps. So I've explained 4 steps to you. Now we have 2 more steps. So the required transformation is what? Okay, what do? You have to get, you got the value of p, you got the value of q, you put it back into this transformation that you've assumed. You've assumed x is equal to p, t plus q. So you put this back into x. So once you do that, you get x is equal to 1 by 2, b minus a t plus b plus a. Okay, so then what do you have? You have f of x. So since you have x already, you have f of 1 divided by 2 b minus a of t plus b plus a. So basically x that you have here that you've written in terms of t is your parameter. Okay, and finally let's just look at this. So dx, when you do that, remember that these values that you have are constants, right? B and a are constants. Okay, they're not going to be functions of x or anything like that. So they are constants, and when you do dx, the only thing that remains is the first constant because you have a t parameter here. Okay, so you have b minus a divided by 2 and you have dt. So this is pretty simple. What do? First step is to assume a linear transformation, a suitable linear transformation. Then you substitute your lower and upper limits. Once you substitute your lower and upper limits, you get your equations. Solve those two equations that you have for P and Q, substitute P and Q back into the transformation that you have assumed, and then you write the function here. So your right function of x here, you would be writing it as a function of t. And then you take the derivative. Why do you need this? Because you have in your integral, what do you have? You have from a to b, say f of x dx. So you need to replace dx as well. You can't just keep it in terms of, if you change this to t, you can't just leave it as dx here, right? So you need to change dx as well in terms of dt so that you can proceed with your integration. Okay, so now since we've done that, what is the next step that we have? We have transformed the integral a b f of x dx to the integral from which has bounds -1 to 1. So now since you've transformed it, you can use your Gauss Legendre integration rule and apply it and find out the value, find out the approximate value of the integral. Okay, so you have g of t dt. We've used this. So yeah, we've replaced this. I showed that you in the previous slide, 1/2 b minus at plus b plus a. And we've replaced here, this entire thing is what? This thing is your dx, which you have replaced in terms of dt. So you have a b minus a divided by 2 into dt. Okay, so you have integral from -1 to 1, g of t dt. So I have transformed the function f of x to something like g of t. Okay, so this is the final result. What is your g of t? Your g of t is f1 divided by 2 b minus at plus b plus a and b minus a divided by 2. Okay, so please write this down on a sheet of paper. Okay, just write this down because this is the value that you need to be able to transform the function into. So your question is going to be from some arbitrary interval like this. You need to be able to transform it into a interval that is bound from -1 to 1 so that you can use the Gauss Legendre integration formula. So let's look at some of the previous questions that were there. Okay, so yeah, so after you get this, you know what to do. You just have to apply the 1 point, 2 point, 3 point formula and get it. Okay, so yeah, before we go to the question, let's just do this. Okay, I want to know how much of attention you guys have been paying. So what kind of a transformation do we use to convert the interval a b to -1, 1? Is it a quadratic function transformation, a linear transformation, a cubic function transformation, or a quartic function transformation? So I will start the poll now. Okay, I will start the poll now. So please plug in your answers fast. I'm only going to wait for a minute. Somebody answered quadratic function transformation. Have you been listening? Please answer fast. 30 seconds left. Three people answered quadratic function transformation. Did we even talk about that here? Did we talk about quadratic function transformation? No, right? 10 seconds left. I will be ending the poll now. Okay, I'm ending the polling. Okay, a majority of you answered linear transformation, which is what I've been discussing here. Why quadratic function transformation? We never even discussed about something like that, right? All these other things are just, this is just to check if you're paying attention, okay? So yeah, this is a linear transformation. What kind of a transformation did we do? Let me just write that down. We did x is equal to pt plus q. This is a linear transformation. Where in this do you have t power 2? When you have t power 2, yeah, it's fine. You're doing a quadratic function transformation, but this is a very linear transformation that you're doing. Okay, so I don't even know why you guys answered that, but yeah, 4 of you guys answered that. Okay, so let me proceed on to the next thing. What are we doing? We're going to be doing a problem for intervals not between -1 and 1. We're going to be doing it for 0 to 1. Pretty easy, okay? The reason why it's easy is because the idea is that you only have to know how to solve the problem. You don't have to really solve complicated problems. This was one of the previous questions that came in, I think, Bangalore Central University papers, okay? Because we never had questions on Gauss integration rule. So evaluate the integral from 0 to 1 dx divided by 1 plus x using the Gauss 3-point formula. Compare with the exact result. Okay, so you do it for the Gauss 3-point formula, and then you calculate this. You do the actual integration, subtract the results, and then get the error that is associated with that. Okay, so what do? Now we have to reduce or change the interval, not reduce, change the interval from 0, 1 to -1 to 1. And then apply the 3-point rule. What is the transformation rule that we're applying? Okay, here we're applying x is equal to 1 by 2 b minus a t plus b plus a. And dx is b minus a divided by 2 dt. We've already done the calculation for this. So these two formulas should be there in your mind. Okay, so you don't have to start from scratch. Okay, of course, if they ask you to do the whole derivation, you have to do it. But if you're just doing it for a problem, you don't have to start from scratch saying x is equal to pt plus q. You don't have to start there. Okay, so what do you have here? A is equal to 0. This is your A, right? This is your A. This 0 is your A, and this is your B. So you have to substitute those values here. Okay, and once you substitute here, basically B is what? B is 1 minus 0. So that's going to be t. Okay, plus b plus a, so that's going to be 0, that's going to be 1 plus 0, so that's going to be 1 here. So t plus 1 divided by 2. You don't have to really remember this formula, because once you get this, you can just do a dx is equal to dt divided by 2. Okay, so it's not necessary for you to remember this, but just write that down just in case. Okay, now what do? Let me just clear this slide. Now, what do? We have to integrate it. So what are you doing? You're transforming this dx into a function that is associated with dt. So what do we get here? Here we got, in your previous slide, we got x is equal to t plus 1 divided by 2. All right. So here you substitute t plus 1 divided by 2. Okay. And once you do that, you should be able to get, so let's just do that. T plus 1 divided by 2. Over here, okay, you take this, you multiply it, so you get a t plus 2 plus 1, so you get a t plus 3 here. And what about your dx? Your dx is dt divided by 2, so 2 and 2 gets cancelled, so you have a dt divided by t plus 3 into dt. Okay, just simple algebra. You should be able to do that on your own. From -1 to 1, f of t dt. So what is your f of t? 1 divided by t plus 3. Now, what have they asked you in the question? They've asked you to do it using your Gauss Legendre 3-point formula. So you substitute it for your 3-point formula. What is your 3-point formula? 5 by 9 f minus root of 3 by 5 plus 8 by 9 f of 0, 5 by 9 f root of 3 by 5. Okay. So you substitute it and you get the calculated. Preferably do it up to 5 decimal points. Why? Because you're doing approximations. So you want to be as close as possible. So preferably do it for 5 decimal points. It's not much. Okay. All you have to do is 1 divided by t plus 3. So it's a very simple formula. So do it. If it is complicated, do it for 3 or 2 decimal points. If it is complicated, but it's very unlikely you get complicated functions. So what is the exact solution? So when you integrate 1 divided by 1 plus dx, you get a ln of 1 plus x, right? So you integrate it from 0 to 1. Once you do this, you get a 0.693147. Okay, so what are you supposed to do to calculate the error? You take this and you subtract it. Okay, so the absolute error is I minus I exact. So this is what you're going to get. So this is the error that's associated with that. Okay, so with this, you're concluding the section 2 part. Okay, so approximating integrals is done. Now, what I want to start off with is section 3, finding Legendre polynomials using recursion relations. This is a very, very, very easy way to calculate your Legendre polynomials. All you have to remember is I will be going through a little bit of revision of your first semester mathematics. I will be going through just to familiarize you guys with your Legendre polynomials and your Legendre differential equations. I will go through a summary of that, and then I will tell you how to calculate those Legendre polynomials. The reason, see, this course is actually supposed to be accompanied by programs and calculating, writing down programs. That's how it's supposed to be done, but that's not the way the university has formulated the syllabus. So this is the best way you can go about it. Okay, so you do the calculation like a computer does. Okay, so you would do iterative methods. You would actually compute what the program is actually going to do each step, and it's boring, I know, but this is the way it's supposed to be going, because of, I don't know, because the way they've formulated the syllabus. Okay, so I will go through a review. I will tell you why we have Legendre polynomials. It's always good to know a little bit about the basic stuff. Okay, and explicit forms of Legendre polynomials that I'm going to be showing you are so that you can check or verify your answers properly. Okay, so probably up to the third order, maybe you can remember it, and I'm sure it's pretty trivial to remember. After that, it kind of gets really complicated. I will show you how they look, and I'm sure you know that as well. Now, what our actual stuff comes down to is from here. Okay, so from here onwards, you would actually need to paying attention. Okay, so we would look at a couple of notations and seed values. We would look at the Bonnet's recursion formula, which is a formula that we're going to be using to calculate Legendre polynomials. And I will tell you why, because all the other recursion formulas that you have, or the recurrence relations that you have, are going to be, written in terms of derivatives, as compared to the Bonnet's recursion formula, which is written in terms of the other, the second and the previous or the penultimate orders that you have. Okay, and then we will be looking at a problem. We will be looking into verifying that problem. And now let's proceed with this. Okay. So how does your Legendre differential equation look? Okay, so this is something that you've seen before. 1 minus x squared y double prime minus 2 x y prime plus n into n plus 1 into y is equal to 0, where n belongs to positive z. Okay, so what did you do in your first semester? You looked at the series solution of the Frobenius method, and you assumed a solution. Okay, and then you started finding out coefficients, right? Okay, and then you started finding out coefficients by choosing the particular, you would get the Legendre polynomials by choosing what these coefficients were going to be like. Okay, so then you looked at a couple of generating functions of your Legendre polynomials. This is how your generating function looks, right? G x of t comma x comma t. You should be pretty familiar with all of this since you've written your first semester at least properly. Okay, so you would write your generating function as this kind of a polynomial and then expand it using the binomial series. Then we come to recurrence relations. Okay, so this is something that we need to remember and we need to note down. Okay, so now there are several different recurrence relations. You have primary and secondary, tertiary, and so on. But what we would be looking at is one of the primary recurrence relations. Okay, so you differentiate g of x comma t with respect to t and with respect to x, and then you have to collect the coefficients of t power n, and that's how you start getting your recurrence relations. Right? So this is a list of all the recurrence relations that you have. Okay, so the primary recurrence relations that you have. Now, what is very peculiar about this is that this guy is not written in terms of the derivatives. Okay, this guy is the actual value, the actual polynomial. So you can write this guy, this polynomial, in terms of a higher order and in terms of a lower order. Okay, so that's what's peculiar about this. So if you're able to do that, then you can, all you have to do is feed all of this into a computer, and you can just keep on repeating this, and you don't have any human intervention that's necessary. Okay, so that's the whole idea of learning computation physics, is so that you can make your computation better and easier, right? By using computers. Okay, so you can understand physics problems by using computers, and you don't have to really put in the effort to calculate all of this. Okay, so please be careful about this. Okay, some people think that it's a product. No, it is not times, it is the actual value x. Okay, be careful about that. So yeah, so if you look at all the other, these are some of the other recurrence relations that you have. All of these are written in terms of the derivative. Okay, at least there's one factor, one way or the other, there's kind of like a derivative that is involved. We will be using a different variant of this. Okay, so this is the Bonnet's recursion formula. We will be using a different variant. Basically, you would have a negative sign here instead of a positive sign and stuff like that. It's all you have. It's pretty simple to remember. Okay, we will talk about that as we approach it. So let's look at some other recurrence relations just to jog your memory. Okay, so we have some things like this. Okay, so we don't really have to look into that. If you look at the other recurrence relations, all of them are written in terms of the derivative. So there's no really a huge point in computing the derivative of the Legendre polynomial. What we're trying to do is compute the Legendre polynomial itself. Right? So yeah, so we will ignore all of that. Now, what are the other things that you guys did? You guys probably found out orthogonality relations. You looked at the completeness of the Legendre polynomials. You looked at a couple of Rodrigues formula and things like that. Okay. So yeah, so all of this comes down to is, why do we want polynomials like this? Okay. So what are these polynomials solution of the Legendre differential equation? And there are going to be physical systems that obey the Legendre differential equation, right? So you want to find out what the solutions are going to be for that particular system, just as we did it for your freely falling body. You saw the freely falling body differential equation, you calculated the solution, or you computed the solution of your freely falling body. Just as that, we're going to have a lot of systems in science and engineering where you need these kind of Legendre polynomials. And why in particular? Because these are orthogonal polynomials. Okay, so yeah, so let's look at this. Okay, so let's look at the different ways in which you can evaluate your Legendre polynomials. The particular way we're going to be talking about is using recurrence relations. But here you can compute Legendre polynomials using generating functions, and I'm sure you must have done this in your first semester. You can find the Legendre polynomials using Rodrigues formula, recurrence relations, which we are going to be doing now. So let me just point that out. This is what we're going to be doing today. And this part is quite not well known, but you can use a Gram-Schmidt orthogonalization, which I think you must have done in your quantum mechanics course. Okay, you must have done it. I'm not sure. Chaudhary ma'am would have taught it to you maybe, but yeah, so you can use that as well to compute your Legendre polynomials. Okay, so why is this guy more reliable? It's quite accurate because you get the actual values from your recurrence relations. You can also compute different orders from your recurrence relations. So if you know the Brown's recursion formula, you can do anything. You can verify the problem, you can compute the problem just using that, and such and such. Okay, so let's just remember these. Okay, so for the 0th order, what is the value of P of n of x? It's 1. Okay, please remember that. Okay, there's going to be a question, so please remember that. Okay, and for your 1, you have x. Okay, so you're going to be working with these two values. So you've got a couple of initial values, let's call it initial values for now. I will change the terminology as we get to the slide. So you've got a couple of initial values, and you're going to be using these initial values in order to do your program. Okay, so all you have to input is 1 and x, and you get the value. Okay, so in your program, what you would be doing is, ideally, you would be submitting these two values, n and x, and then it would start calculating the values for you. Okay, so let's remember 1x, and let's remember this. Let's remember 1 by 2, 3x squared minus 1. Okay, so please can you note this down? Okay, so we're going to be having a problem. So I want you to note this down. For the second order, you have 1 by 2, 3x squared minus 1. Okay, so please note that down. I hope all of you have taken that down, because we have a question that's going to be coming up towards the end. Okay, so let's look at the Legendre polynomial graphs. Let me just explain the first 2 or 3 maybe, and after that it kind of goes haywire. So what do we have here? So this is your Pn of x. So what did we say? The 0th order had something like this. So you just had a one line. Okay, so we had P0 of x is equal to 1. P1 of x is equal to what? X. P2 of x is equal to 1 by 3. You had 3x squared minus 1, right? So this is what we had. So you have this one here. Here you would have your x. So where is that guy? This is your x. Okay, I should have probably chosen a different color, but I hope you get it. This is your x, and then the next one goes all quadratic, so it's going to be like this. Okay, so this is the green line is your P0 of x. P1 of x is this. Okay, so you have an x here. This is your P1 of X, a little bit more slight version of green, and P2 of X is just your quadratic. Okay. It's not 1 by 3, is it? What is it? Is it 1 by 2? Yeah, it's 1 by 2. Okay, thank you, Nathan, for pointing that out. The thing is 1 by 2. Somebody's paying attention. Okay. So here you would have 1 by 2, 3x squared minus 1. Yeah. As your P2 of X. Okay. So let's proceed to the next one. Okay, so what are the precursors to solving the problem? Yeah. What are the precursors to solving the problem? What do we have here? We need the Legendre polynomial. Okay, so we need the order of the polynomial. We also need the point at which it needs to be evaluated. So what did I say? When you're going to be doing your program, which we're not going to be doing when you write the program, if you want to write the program, you would be inputting these values. You have n, which is the order of the polynomial, and x, which is the point of the evaluation. So that's your input. But you also need something else. You need the initial conditions that I said, which are not actually initial conditions. Those are called as seed values. Okay. So let's look at that. So there are two base cases. So if your n is 0, what is the value of the polynomial? It is always going to be 1 irrespective of the value of x. Please note that. It's always going to be 1 irrespective of the value of x. If you have n is equal to 1, then the value of the polynomial is always x. Okay. So what are these called? These are the seed values. So you need something to start off your program with, and then you would have the seed values. Okay, so this is how you're going to be working. You're going to be working like a computer. You're going to be starting off with the seed values. You're going to be given these n and x values, and you will proceed further with that. Okay, so this is a slightly different variant of the Bonnet's recursion formula that I told you about. Okay, the three-term recurrence relation. So you have n, p of n, p, nth order of x, 2n minus 1. This is not multiplication. Please note that. Okay, so last time when I did this, somebody said this was a product. No, it's not that. It's an x. Okay, it looks like a product, but it is x. Pn minus 1 of x minus n minus 1 pn minus 2 of x. Okay, so what have you done? You've been able to express the nth order in terms of the previous two orders. You've been able to express this in terms of n minus 1 and n minus 2. Okay, so now we are all equipped to work on the problems. Okay, so let me just start off with another poll. What are the two seed values used to calculate Legendre polynomials? So let me just start off with this poll. Poll number 18, right? Poll number 18. And we have that. So please click in your answers fast. Okay. What is this, guys? Like I just explained and told you about what you require. I told you it's 1 and x. The seed values are 1 and x. 30 more seconds. I am telling you the answer right now, and you still end up clicking the other options. Oh God. I am telling you the answer is 1 and x, and you still end up clicking other options. This is just really bad. Okay, so have all of you voted? I'll wait for about 5 more seconds. Okay, so I'm ending the polling now. I just explained to you why we need to be able to equip ourselves with a couple of parameters so that we can work on the problem, right? I told you what you need. You need the value of x. You also need the value of n. You need the order that you need, and you also need the point of evaluation. Then I told you that you need two seed values, and the seed values are going to remain the same irrespective of whatever parameters that you have, right? Of course, the point of evaluation would differ in different problems, but still, I told you the values are 1 and x. I still end up having people saying 2 and x, 3 and x power 2. I mean, like what is happening? Pay attention, please. Okay, so let's proceed on with the problem. Okay, so this is how your problem is going to be. Calculate the value of the third order Legendre polynomial at x equal to 5. So what is the value of n that you have here? Because I've said it's third order, n is equal to 3. Okay, so use the Bonnet's recursion formula, npn of x is equal to 2n minus 1 into p, this is not into x, pn minus 1 of x minus n minus 1 pn minus 2 of x. Okay, so what do? You're given that n is equal to 3 and x is equal to 5. Okay, now what is going to happen here is that you're going to be writing it in terms of the zeroth. You need to be able to reduce this in terms of the zeroth order and the first order. Why is that? Because those are the true seed values that you know. Your seed values are what? You have P0 of x equal to 1 and P1 of x equal to x. Okay, so these are the two seed values that you have. And you need to be able to reduce this to that. So you need to do it as an iterative way. Ideally, we would use a for loop and do it in your program. Okay, so that you would be able to reduce the value of the Legendre polynomial and compute it. But here we're going to do it manually. Okay, so you will write the third order in terms of the second order and first order. You write the second order in terms of the first order and zeroth order. You know the first order already with you, which is x. Okay, so you reduce whatever order that you are given into zeroth order and first order. That is the whole point. So you take whatever order that you're given, say you're given order 3. Okay, you reduce it. You will be able to reduce it using the Bonnet's recursion formula into 2 and 1. Once you do that, once you get 2, you should be able to reduce that in terms of 1 and 0. So you know 1 here, you know 1 and you know 0, and you'd be able to compute that. Okay, so let's just go through this in detail. Okay, so here you would have 3p3 and you have 5, which is your point of evaluation. 2 into 3 minus 1 over here, 5 over here, and then you would have p3 minus 1. So this is the second order. Okay, and here you would have the first order. So first order is a seed value. So you know p1 of 5 is equal to 5. Why is that? P1 of x is equal to x. So you substitute that over here, and all you're left with is to compute the second order now. Okay, so you will use the same relation, okay, and you will do 2p2 of x, okay, equal to 2 into, what is your n? 2 minus 1 into, you have a 5 into p, you would have n minus 1, that is 2 minus 1, which is 0 of x. And then you wouldn't have to, you would have, wait, 2 minus 1 is 1. Okay, so 2 minus 1 is 1, and then you would have 2 minus 1 again, p of 2 minus 2, which is the 0th order, and then you would have to stop because you're attaining your z values again. So what is this guy? This guy is 5, but still it's going to be 1. Irrespective of the value of x, you still end up getting 1. This one is going to be 5. Okay, why? Because p1 of x is equal to x, so p1 of 5 is equal to 5. So that is what you will get in your next slide. Okay, so the next slide, it's a very simpler version of what I've written down. Okay, all the calculation, and you should be able to get your third order. All this is algebraic stuff. Okay, so you should probably, there's going to be a problem associated with this. And I hope you've taken down the second version of your Bonnet's recursion formula. Please take this down. Npn of x is equal to 2n minus 1, x pn minus 1 of x minus n minus 1 pn minus 2 of x. So in the in one of the Google forms that I'm going to give you after the class, it's going to be asked. Okay, there's going to be a problem that is asked. I hope I've explained this at length. I have just neglected your algebraic manipulations because we're starting to slowly run out of time. Okay. Okay, so now, what do we have here? We have, let's say you remember, okay, so let's say you remember the explicit form as 1 by 2, 5x cubed minus 3x. Okay, if you remember the explicit form, all you have to do is take n and 3, which is given to you, and substitute the value, and you find out that p3 of 5 is equal to 305. Okay, here you have 305, so you compare it, and then you say, okay, fine, I know that How do you check your answer is correct? You check your answer is correct using this. Now, if you do not remember this value, okay, if you do not remember the explicit form, what do you have to do? It's pretty simple. All you have to do is do this guy, okay, iteratively, not for just x equal to 5, but do it for x equal to x itself, okay? So you do the same thing for x equal to x, and you should be able to get this, oh God, okay. You should be able to get this value. You should be able to get this, this function from just substituting x equal to x rather than x equal to 5. Okay, so if you don't remember the explicit form of the Legendre polynomial. Okay, so let's look at this. Another question that you can have is pretty much simpler than the first one. Find the explicit form of the second order Legendre polynomial P2 of x. Okay, so we just discussed this. We said it's 1 by 2, 3x squared minus 1. Okay, so what do you have here? This is your different version of your recursion formula. I hope you realize that. It is not the 2n minus 1 form. It is a bit of a different version. You can use either, okay, because eventually it's the same thing. It's just that you put n is equal to n minus 1. Okay, so once you substitute all of these values in, what do you substitute? You substitute n is equal to 1. You also substitute x is equal to x. And then what do we have here? You have your seed values p1 and p0, right? So you substitute your seed values and you get this form back. Okay, so that is another problem that you could get. Okay, so please, I hope you've taken this formula down, 1 by 2, 3x squared minus 1, right? Because the next question that we have is using the explicit formula shown in the previous slide, okay, not shown above, shown in the previous slide, calculate the second order Legendre polynomial at the evaluation point x equal to 3, okay? So calculate that and you plug in your answers. I will start the poll now. Maybe I can give you a little bit more extra time because you have to do some math here, which is trivial, but still give you a bit of extra time. So please calculate that and plug in your values. If you guys don't know what the formula is, the formula is 1 divided by 2, 3x squared minus 1. That is Pn, P2 of x. P2 of x. So all you have to do is plug in what? Plug in the value x equal to 3 in this function. Let me just write this a little bit more neatly. 2. Seriously, who answered 1? Who answered 26? What is this? Please plug in your answers fast. I will wait for maybe 15-20 seconds. This is pretty trivial. I don't understand why you're answering the others like 26, 27, 1. Why are you answering them? All you have to do is take this function and substitute x equal to 3. I'll wait for 10 more seconds and I'll end the poll. In fact, I've actually just told you what the answer is going to be. Kind of like eliminated all the other options for you. And you still end up plugging in those wrong options. Okay, so I'm going to end the poll now. Sharing the results with you guys. I do get who entered I get the names of people who entered the correct values or the wrong values. Okay, I get the names. So it's not something that is anonymous. Okay, I do get the names. So let's just do that for those who did not understand how this whole thing works, right? X is equal to 3. What is your second order thing? It's 1 minus 2. 3x squared minus 1, which I wrote above here again. So you have 1 by 2, 3 into 3 into 3 minus 1. That should be a 27 minus 1, right? 27 minus 1. So you get a 26 by 2, which is what? 13. Okay, I hope you get that now, hopefully. So I will stop sharing the results and I will ask you one more question. And I guess that would be it for today. Does the value of the 0th order Legendre polynomial change based on the value of x? Please read it carefully. Does the value of the 0th order Legendre polynomial change based on the value of x? I will start the poll now. Yeah, these are very simple questions and you should be able to answer them using whatever I've just discussed. Okay. Okay, somebody answered yes. How does it change? Maybe the people who answered yes can explain it to me. Okay, 30 seconds left. This is a very trivial question and we've been discussing about P0 of x for a long time. It's one of the seed values. It's the first seed value that you use. So what is P0 of x? P0 of x is 1. So irrespective of the value of x, it is going to give you the value 1. It does not change. It's a constant for whatever value of your point of evaluation that you use, whatever value of x that you use. Right? Still people end up saying yes. There's only so much a person can do. Okay, so I'm going to be ending the polling now and I will show you your results. Okay, majority of you answered no. Good, well and good. Let me just write that for you guys. Okay, how does your P, let's say P0 of x, what was the seed value? The seed value was 1. P1 of x I can understand. You can say x, so based on the value of x, it can change. But P0 of x, irrespective of the value of x, is going to be 1 itself. Whatever value of x that you use, let's plug in 1, you end up getting 1. If you plug in 2, you end up getting 1. If you plug in 3, you end up getting 1. So irrespective of the value of x, you end up getting 1. So does the value of the 0th order Legendre polynomial change based on the value of x? No, it does not change. Okay, so get that. Okay, so today we've kind of like concluded with this.